In the first part of this lesson, we discussed the disk method of measuring the volume generated by revolving an area around an axis. Now, the disk method will work only if that area that you revolve is in contact with the axis. Then only you will generate a disk. Now, what happens if an area is actually not in contact with the axis? Now, this is the axis that I'm holding, and this is the area. There is a space between them. Now, what kind of a solid is generated if I revolve this area now about this axis? Can you figure out? Now, when this revolution occurs, it is going to leave a big hole at the center. Is that right? So, we are not generating disk in this case, but we are generating a washer. Now, what is a washer? I'm sure you have seen washers used for fixing things. Now, here is an example of a washer. If you notice, there's a hole in the middle. Now, you have the graph of one function and the graph of a second function. There is an area enclosed by the graphs of two functions, and it is that area that we revolve about an axis, and it generates a washer. Now, in finding the area here, now remember, in the case of a disk, the area of one face is the area of the circle, which we said is pi r squared. Now, how about the area of this face of this washer? What we need to do is, we need to take that full disk, which has an area pi r squared, where r is the distance from the center to the edge of the outer circle. Now, from that, take away the area of the hole. If the area of the hole, if the radius of the hole is, say, lowercase r, and the radius of the whole disk is uppercase R, then pi r squared is the whole area, which is r is the uppercase R. Pi times uppercase R squared is the whole area, and pi times lowercase r squared is the area of the whole. So what you do is, you take away the area of the whole from the area of the complete disk. That will give you the area of the washer. In other words, pi times uppercase r squared minus pi times lowercase r squared. Alright, we're going to discuss that in this lesson. Alright, so we said when the area revolved is not in contact with the axis of revolution, we cannot generate disk. Now, let's take a look at one such example. Consider the area enclosed by the graphs of f of y equal to y squared and g of y equal to square root of y. They're functions of y. Alright? What is the graph of f of y equal to y squared? That is the graph of f of y equal to y squared. Remember, f of y equal to y squared is the same as x equal to y squared. And can you express that as a function of x? If x equal to y squared, then y equal to square root of x. That's the graph of this. So, this is the graph of x equal to y squared or y equal to square root of x. Alright. Now, this is the graph of x equal to square root of y. Now, can you imagine the area enclosed by this? That's the area enclosed by this, and we need to revolve this area, let's say, about the y-axis. Now, again remember, you can generate disk only if the area is in contact with the axis of revolution. Now, this is the way we generate a disk. But in this case, this area is not in contact with the disk. So what do? What kind of a solid will be generated by revolving this area about the y-axis? Can you visualize? If this area is revolved about the y-axis, what kind of solid will be generated? Well, let's approach this the same way as we did with the disk. Take a strip of area dA of width dy. Now, this is the area dA and the width of that is dy. And you notice that this area is not touching the axis of revolution. Now, revolving this area about the y-axis generate a, is that correct to say, generates a disk of width dy? Yes, it generates a disk with a hole at the center. Now, I want you to picture this. Take this area and revolve it about the y-axis. Now, let's see if I can find one of the things that... Alright, now here is that area and I need to revolve it about the y-axis. You see that there is a space there. So if you revolve this about the y-axis, it is going to be like this, which means it is going to leave a hole at the center, and therefore it is going to generate a washer. That's right. So it will be something like this. This is the washer. So look at that again. That small area dA, when revolved about the y-axis, generates this washer. And the thickness of the washer is actually the width of that area, which is dy. So we call this a washer. Now, the outer radius of this washer. What is the outer radius of the washer? What is the meaning of the outer radius? The distance from the axis of revolution to the edge of that washer. That is the outer radius. And we're going to call it uppercase R, R of y, equal to G of y minus 0. You see, this is G of y. And the distance of this graph from the y-axis, all of that is actually G of y. That means this whole distance is the outer radius. I hope you understand that. Pay special attention to that. Now, when this whole area is revolved, the outer radius is this distance, isn't it? And that distance is G of y minus 0. 0 is x equal to 0. So, R of y equal to G of y minus 0, which is actually G of y. Alright, so there you have, this is the outer radius, and that is R of y equal to Gy. Now, what is the inner radius? Inner radius is the radius of this hole. The radius of the hole is this. And what is that distance? This is the graph of the function f of y. And therefore the distance of that graph from the y-axis is f of y. So the lowercase r of y is f of y minus 0, which is f of y, and that is this distance. So you must understand and distinguish these two radii. A washer has an outer radius and an inner radius. In this case, the outer radius is G of y and the inner radius is f of y. The outer radius is represented by the uppercase R. The inner radius is the lowercase r. And now, what is the volume of that washer when you revolve it about the y-axis? What is dV, the volume of that washer? Now, let me show you the disk that I used. If you look at this disk, you can see this is a washer, isn't it? Yes, you can see the hole there. Now, what is the volume of this disc, of this washer? Well, if you take the complete volume of the disc, including the hole, and then subtract the volume of the hole, is that right? In other words, the complete volume will be pi big R squared times the width, and then subtract pi small r squared times the width. And that will give you the volume of the washer. So, volume of the complete disc. The complete disc means the solid and including the hole. What is the volume of the complete disc? Pi times uppercase R squared dy. Now, that will give you the complete volume of the disc. Now, take away the volume of the washer, of the hole. What is the volume of the hole? The volume of the hole is pi times lowercase r squared times dy. dy is the thickness of the disc. So, the volume is the face area multiplied by the thickness. For the entire disc, the face area is pi times uppercase r squared and multiplied by dy. So the volume of the complete disc is pi uppercase r squared dy. The volume of the hole is pi lowercase r squared dy. Therefore, what is dV? The volume of the washer. The volume of the washer is the volume of the complete disc minus the volume of the hole. That will be pi times uppercase r squared dy minus pi times lowercase r squared dy. And you can factor out pi, and so dV equal to pi times uppercase r squared minus lowercase r squared times dy. Alright, if you notice there is a small error in here, can you spot that? That square must be for this radius. That's right. And this dy is going to be multiplying the whole of the quantity. That's very important. This dy multiplies the whole of this. In other words, pi times r squared minus r squared, uppercase r squared minus lowercase r squared in a parenthesis times dy. Okay. Now, in order to find the complete volume generated by revolving this whole area, we integrate the dV. We integrate dV from y equal to c to y equal to d. So this is y equal to c and that is y equal to d. Is that right? That's the limit. So this whole area, when revolved about the y-axis, generates a volume V, and that is obtained by integrating dV from y equal to c to y equal to d. And how do we obtain c and d? C and d can be obtained by setting f of y equal to g of y. Let's do that in this case. What are the points of intersection? The points of intersection occurs where f of y equal to g of y or y squared equal to square root of y. And that happens at y equal to 0 and y equal to 1. So this is one point of intersection and that is the other point of intersection. So your value of c is 0 and the value of d is 1. And so V equal to pi times integral 0 to 1 uppercase r squared minus lowercase r squared dy. Now remember, our uppercase r is g of y and our lowercase r is f of y.